Hi everyone, this is going to be the first video for Unit 5, and what we're going to be talking about is analyzing a function using its derivatives. So we're going to be using information we have from a derivative to describe features of an original function. The good news of this is if you were pretty good at interpreting those velocity graphs, a lot of the ideas are going to be pretty similar here. So we're going to talk in general about some of these big ideas and then look through lots of examples. So when we're connecting a graph with its first derivative, here's what we need to know. So the first derivative of a function tells us about the slope of the original function. So this means we can tell when a function is increasing or decreasing by looking at the sign of the first derivative. So a function is increasing when it has a positive slope. And we say that a function is increasing because f prime of x, so the derivative, which is the slope, is greater than or equal to 0. So we'll say a function is increasing because f prime of x is greater than or equal to 0. On the other hand, a function is decreasing when it has a negative slope. And we justify that a function is decreasing, and we say because f prime of x is less than or equal to 0. Now, a new vocabulary term that we have, these are called critical points. These are just places where the slope is 0 or undefined. And when we're justifying where a critical point occurs, we'll say that a function has a critical point because f prime of x is equal to 0 or f prime of x does not exist. So what we're going to do is we're going to look at a couple of graphs. One is going to be the graph of our original function and one is the graph of the derivative, and we're going to be looking for three things: where these graphs, or where the function I should say, is increasing, where it's decreasing, and where those critical points are. Alright, so first we're just going to look at the function itself. And again, the question is, where is f of x increasing, decreasing, and then where are the critical points? So when we're looking at a graph of f of x, we said it's increasing wherever it has a positive slope. So on my graph of f of x, I can see that it has a positive slope here and here. So we would say f of x is increasing from 0 to pi over 2, and then 3 pi over 2 to 2 pi, because it has a positive slope. And by convention, when we're talking about increasing or the first derivative, we're always going to use closed intervals or closed brackets. So we're increasing wherever it's in yellow, where it has a positive slope. It's going to be decreasing now wherever it has a negative slope. So we have a negative slope from here to here. So in interval notation, we'd say it's decreasing from pi over 2 to 3 pi over 2. Alright, and then the last thing I need to look for are our critical points. Now, we said critical points are places where the slope is 0 or undefined. Now, if I'm looking at this graph, there aren't any sharp corners or cusps or anything that would cause my derivative to be undefined, but I do have two places where the slope would be 0, right? What I'm looking for there are horizontal tangents, and those are going to happen here and here. So I've got two critical points. So critical points happen where x is equal to pi over 2 and 3 pi over 2. So it's pretty easy to analyze when we're looking at the graph of the regular function. What we also have to be able to do, though, is look at f prime of x and still tell these same things. Looking at f prime of x, I still have to be able to decide where my original function is increasing where it's decreasing, and where it has critical points. Again, and the idea here is I have to look at f prime of x and use that information to tell about f of x. So let's think about this. We said f of x would be increasing wherever f prime of x is greater than or equal to 0. So if this is a graph of f prime of x, I'm going to make a note here. It's increasing where f prime of x is greater than or equal to 0. That means wherever f prime of x is above the x-axis. So we would be looking here and here. F is increasing on those two intervals. And again, those two intervals are from 0 to pi over 2 and 3 pi over 2 to 2 pi. So because I was looking at the graph of f prime, I had to see where it was greater than or equal to 0 to determine where my original function was increasing. For decreasing, we said we're decreasing wherever f prime of x is less than or equal to 0. So for my graph of f prime here, I'm going to look where it's less than or equal to 0, which means everywhere it's below the x-axis, which is going to be this interval here. So from pi over 2 to 3 pi over 2. And then the last thing we'd be looking for again are those critical points of f. We said that's where f prime of x is equal to 0. Well, f prime of x is equal to 0 here and here. So at x equals pi over 2 and 3 pi over 2. So you can see we got the same information about the function, but one was by analyzing the function itself, and one was by analyzing the graph of its derivative. All right, so let's look at some problems and apply this. So our example says, let f of x have the graph shown. So the important thing to note here is that this is f of x, our original function. They're asking which of the following is a possible graph of f prime of x. So I have to connect the original to its derivative. So first, I'm going to start with looking where f of x is increasing. And that's going to happen from here to here. So about from -2 to 1. So since f of x is increasing from -2 to 1, that means f prime of x is positive on that interval. So I need to look for an option where f prime is above the x-axis from -2 to about 1. So if I look here from -2 to 1, I'm above the x-axis, so that's a possible choice. From -2 to 1, I'm also above the x-axis, so that's a possible choice. Now here, from -2, this starts below the x-axis, which I know can't be true, so that is out. And then for D, again, at -2 here is below the x-axis, which we know is not true. So now I'm down to two choices. So let's look at our other behavior. So I am decreasing, my original function is decreasing from -infinity to -2. So that tells me between -infinity and -2, my derivative should be below the x-axis. So if I look from -infinity to -2, this one is both above and below. So that can't match. So that leaves me with choice B. And again, let's go through this here. Where I'm increasing here means that f prime of x had to be greater than or equal to 0. When I look at choice B, I see that over the same interval from -2 to 1, I'm above the x-axis. F prime of x is positive. From -infinity to -2, this is decreasing, which tells me that f double prime of x is less than or equal to 0. And that's what I see happening here. I'm below the x-axis. Now, we could keep going. This is also decreasing from here to about here. It's going to turn upwards in a little bit. Over that same interval, I see that I'm below. And then when this turns positive again, this is above the x-axis. So that's why B is the correct choice. Now, number 2 is opposite. This graph shows me the derivative of f and is asking which could be the original. So let's take a look here. The derivative of f. So what this is telling me is that f prime of x is greater than or equal to 0. On the intervals, it looks like from negative infinity to negative 1 and from 1 to infinity. So that means on those same intervals, if f prime of x is greater than or equal to 0, f prime of x should be increasing. So that's the first thing I'm going to check. If I look at my original graphs, for a from negative infinity to negative 1, let's see, it looks like I'm increasing, but this actually goes from negative infinity to maybe like negative a half. So that won't work. For b, from negative infinity to negative 1, I'm increasing, and then again from 1 to infinity, so that's a possibility. Here, from negative infinity to negative 1, it's actually decreasing, so I know that can't be right. Here, this is always increasing, which I know is not going to be true. It's only over these two intervals, so D is out. And then E is always decreasing, so that can't be true. So B must be our answer. Now we can verify. If I look at this interval between negative 1 and 1, I have that f prime of x is less than equal to 0 between negative 1 to 1, which tells me that f of x is decreasing on that interval. And if I double check with B, that's actually what I see. I'm decreasing between negative 1 to 1, so B is in fact the correct answer. And this type of problem will show up a lot on the multiple choice section of the AP exam. All right, so for our last page of notes here, we're going to be looking at kind of three different scenarios. One is the graph of the function, one is the graph of the derivative, and then one is if we're given a function itself. And we're always going to be looking for the critical points, intervals where we're increasing, and intervals where we're decreasing. So let's start with the graph of f of x. If I'm looking for critical points, I know that's where f prime of x equals 0 or doesn't exist. So where does the derivative equal 0 or not exist? And I'll do these in green again. So again, I don't have any sharp corners or cusps or discontinuities that are going to make me not differentiable, but I will have the derivative equal to 0, or that slope of the tangent is going to be 0 at these kind of turning points here. Right? If I drew in my tangent, it would be horizontal, which gives me a slope of 0. So I have critical points at x equals negative 1 and 0. I'm increasing wherever f prime of x is greater than or equal to 0, or wherever f has a positive slope. So that's going to be on this interval and then on this interval. And we're going to draw these in. I think you have this in your notes, but these should have arrows. So I'm increasing from negative infinity to 1, and again I use closed brackets, and then again from 0 to infinity for my increasing. And then lastly, for decreasing, we're looking where f prime of x is less than or equal to 0, or where it has a negative slope. And so we can see that happens here in between negative 1 and 0, so we're going to write that in our interval notation. So again, it's pretty straightforward when we're looking at the graph of the function itself. So what we're going to do now is look at a graph of the derivative. But it's the same definitions here. So for critical points, we're looking where f prime of x is equal to 0 or does not exist. And I'm going to draw these arrows. So now my derivative here, this graph is f prime of x. There aren't any points where it's undefined. We can see we've got a smooth continuous curve. So really I'm focused where f prime of x is equal to 0. It's equal to 0 here where it's crossing that x-axis. And so we can see we've got x equals -1 and 0. For my intervals of increasing, I'm looking out for places where f prime of x is greater than or equal to 0. So that means it's going to be where I am above the x-axis. That's where f prime is going to have positive y values. So we've got from -infinity to -1, and then from 0 to infinity. And then lastly, decreasing is where f prime of x is less than or equal to 0. So that's going to be where it has negative y values. And so that's going to be between -1 and 0. So actually what you can see happening here is this graph f prime is actually the derivative of this graph. All right, now we're going to look at how to do this same justification if we're just given an equation. So a lot of times you'll be given the equation for a function and you'll have to analyze these things. So I know this all has to do with the first derivative. So that's what we're going to calculate first. So I'm going to calculate f prime of x. That is going to be, let's see, 6x squared plus 6x. And we're going to start with the critical point. So I'm going to start by setting this equal to 0. So I'm going to factor out a 6x. And then I get x plus 1. And that's equal to 0. So that means either 6x is equal to 0 or x plus 1 is equal to 0. Which tells me that my critical points are at x equals 0 and x equals -1. So now I have to figure out the intervals where my derivative is positive and where it's negative. And so here's where we're going to make a table very similarly to how we did when we were analyzing velocity. So I'm going to take my function, we're looking at f prime. I want to know the sign of f prime. Now, I know the domain of this function is all real numbers. So my far left endpoint is going to be -infinity. I'm going to put in my -1, my 0, and then again at the far right endpoint, that would just go off to infinity. We don't really have a closed endpoint. And now I'm just going to analyze the sign in each of these intervals. So if I plug in, let's say -2, 6 times a -2 is negative. -2 plus 1 is negative. A negative times a negative makes that a positive. In between -1 and 0, if I do -1/2, that's going to be 6 times -1/2 is a negative. -1/2 plus 1 is positive, so I get negative times positive is negative. And then lastly, let's say I pick 1 for this interval. 6 times 1, that's positive. 1 plus 1 is positive, so that gives me positive. So now I can figure out where I'm increasing or decreasing. Increasing, we said, was where f prime of x is greater than or equal to 0. So it's going to be everywhere the sign is positive. And what I know then is that's where my graph is increasing. So if I write that in interval notation, I have -infinity to -1, and I have from 0 to infinity. And if we were asked to justify, this actually would be our justification. We'd say it's increasing on these intervals because f prime of x is greater than or equal to 0. For decreasing, we're looking where our derivative is less than or equal to 0. So I'm looking for where that's negative. So my interval would be between -1 and 0 because f prime of x is less than or equal to 0. So for day 1, we're just working with these three key features. You'll have a day to practice these, and then we'll add some key features by looking at the second derivative. All right, go back and rewatch any sections that you need to, and definitely when we start class we can go over any questions that you have. All right, thanks for watching.